Hello, my name is Xiaohan Liu. The paper I will be presenting in this video is titled Face-Based Voice Conversion: Learning the Voice Behind a Face. In this work, we introduce a novel idea of generating different voice styles from different human face photos with a voice conversion backbone. Voice conversion aims to convert the speech of a source speaker to that of the target speaker without changing the linguistic information. In recent years, zero-shot voice conversion gains popularity, since it can convert speech to any unseen voice. This is a typical structure of an autoencoder-based voice conversion model. In the training stage, speaker and content information are extracted from input audio respectively, and combined to reconstruct the original speech. In the inference stage, the well-trained encoders can extract content information from source speaker and extract speaker information from target speakers to achieve voice conversion. As facial appearance and voice style is highly related, one's voice can be speculated from how they look. In our work, we propose a new method of voice conversion, which directly synthesizes the target's voice according to the face images, instead of the speech corpus of target speakers. In fact, the face-based voice conversion is able to facilitate many unique applications with its flexibility on altering the voice style, such as personalized voice assistant and revoicing in filmmaking. One intuitive way to achieve face-based voice conversion is to change the acoustic features of the target speaker to the facial features. However, it will cause two main challenges. The first challenge is face-speech transformation. The facial images and speech are cross-domain. Although part of their dimensions are related, there are some facial features that are irrelevant to speaker's vocal style. As such, voice conversion can easily be confused by useless types of information and cannot learn a precise mapping between multimodality of the same speaker. Such phenomena cause the model to generate only an average timbre beyond all speakers. The second challenge is noisy clean transformation. Existing deep learning-based voice conversion works are conducted on laboratory collected speech datasets with relatively simple content and without photos of the speakers. In contrast, the datasets containing both faces and speech are mostly collected from in-the-wild environment, and the converted audio results from these noisy datasets usually have a lower audio quality. As there is no available dataset containing speaker faces and clean speech at the same time, we want to leverage both laboratory collected and in-the-wild speech datasets to get better results. To address these two challenges, we propose an autoencoder-based voice conversion framework, as known as FaceVC, along with a well-designed training strategy to attain knowledge transfer from multimodal input. Specifically, FaceVC consists of a face encoder, a visual-to-audio transformation, and a reference generator. The face encoder extracts speaker-related facial features and forms a visual speaker distribution. The derived speaker embeddings from training data should be able to accurately estimate the representations of new faces in the latent space to attain zero-shot conversion. As such, the proposed face encoder contains two modules: facial feature extraction and face voice feature reparameterization. In facial feature extraction, initial speaker embeddings are extracted by pre-trained FaceNet model. FaceNet projects facial images to a latent space with the distance reflecting face dissimilarity. Also, to maintain face angle consistency for better learning of the speaker embeddings, we applied face alignment on face images. After deriving the speaker embeddings from FaceNet, we further enhanced them by applying the self-attention mechanism. Self-attention aggregates similar information from different facial dimensions and reweights them according to their influence on voice styles. The enhanced hidden feature are expected to only carry the part of generating timbre of the target speaker and then pass into next module. In face-voice feature reparameterization, we adopt a reparameterization approach to introduce stochasticity into the network. This process has two advantages. First, since any point in the continuous Gaussian distribution is representative, the model can locate the unseen faces on any possible point on speaker distribution, which performs zero-shot conversion. Second, the reparameterization procedure transforms input distribution into Gaussian distribution, which helps cross-domain mapping. Next, visual-to-audio transformation warps the visual speaker distribution to the vocal speaker distribution. Lastly, the reference generator produces converted audio with content encoded from speech and voice styles sampled from speaker distribution. In addition, to address the noisy clean transformation challenge, we propose a three-stage training strategy to leverage both laboratory collected and in-the-wild speech datasets. The goal of this training strategy is to synthesize high-level audio quality of laboratory collected speech from in-the-wild data. Stage 1 includes a face encoder and a pseudo generator, and is trained on in-the-wild data. In this stage, we conduct a normal voice conversion training, except that the speaker information is encoded from human faces by the proposed face encoder. The corresponding latent space allows interpolation on voice styles. The objective function is to minimize the reconstruction distance of the speech spectrogram and content embedding, as well as the GE to E loss on the facial speaker embedding. The GE to E loss here aims to maximize the embedding similarity for the same speaker and minimize the similarity among different speakers. The goal of this stage is to acquire a well-trained face encoder that brings out the facial features which are beneficial to generate timbre. In stage 2, a voice conversion model following the AutoVC framework is trained with laboratory collected datasets and consists of a speaker encoder and a reference generator. The input audio are first passed into speaker encoder to extract voice features. It's worth noting that the extracted voice embeddings are fed into the face voice feature reparameterization to form a vocal speaker distribution. After, the reference generator can synthesize clean speech with speaker embedding sampled from vocal speaker distribution. The loss function is simple spectrogram and content reconstruction loss. The goal of this stage is to provide the accurate speaker embeddings for stage 3 and extract content from clean speech for inference. Finally, stage 3 is trained on in-the-wild dataset. Face encoder from stage 1 and speaker encoder from stage 2 are fixed. Face encoder extracts speaker embedding from facial domain, and speaker encoder extracts speaker embedding from acoustic domain. The visual-to-audio transformation is trained at this stage to act as a connecting bridge between these two speaker embeddings. The training objective here is to minimize the distance between the transformation output and vocal speaker embedding from the speaker encoder. This stage aims to learn the implicit relationship between the facial features derived in stage 1 and the speaker embeddings offered in stage 2. During inference, Face VC can achieve high audio quality voice conversion with speaker information from face images. Before demonstrating the experiment result, we introduce two datasets that are used to realize Face VC. For laboratory collected dataset, we choose VCTK corpus. VCTK is the most popular used dataset in voice conversion task. It performs high audio quality, yet has no speaker faces. For in-the-wild dataset, we choose LRS3 TED dataset. It's collected from TED Talk videos, so it includes face information, but audio quality is relatively bad. Then, we want to show some synthesized audio from Face VC.
But who said the positive?
But who shot the president?
But who shot the president? But who shot the president?
The audios demonstrate that Face VC can generate different voice styles according to one's facial appearance. For more audio samples, please refer to our demo website. In the first experiment, we want to show the model robustness of voice conversion models. We conduct MOS tests to evaluate the converted audio sound quality. We'll show the audio samples of AutoVC as reference. This is from VCTK,
Please hold there.
and this is trained on LRS3 TED. This result reveals that voice conversion models are not robust to the in-the-wild dataset since they cannot achieve comparable results with laboratory datasets. Next, we show the power of the proposed three-stage training strategy. The figure presents that stage 1 has the lowest MOS score among all stages, since it is trained on in-the-wild datasets. For stage 2 and inference stage, audio quality performance is comparable.
Because we do not need it.
Stage 2 can reach good audio quality results because it is trained on laboratory collected datasets. As for the inference stage, it takes style codes from stage 3 and content codes from stage 2, which transfer the audio quality from stage 2. Except for audio quality, whether Face VC produces accurate timbre is also concerned. It is challenging to verify how facial features correspond to voice styles in the real world. In this case, we plot the speaker embedding extracting from converted audio and its target speech to show the distribution. From the figure, we can see that the speaker embedding extracted from converted audio is near their true voices. It serves as a piece of evidence that our model can generate prototypes of speaker styles from faces. In conclusion, we summarize our contributions as follows. First, we propose Face VC, which is the first voice conversion work that can generate personal voice style from facial representation. We construct a face encoder and a visual-to-audio transformation to form a speaker-related distribution from faces. Also, we introduce a three-stage training strategy to make synthesized audios from in-the-wild dataset speak high audio quality content. Experiments demonstrate that facial appearance can be a source of voice style and that converted results achieve good audio quality. We believe that the proposed voice conversion from the face can open up a new research direction of face-voice relation and widen the application of speech synthesis. Thanks for your listening.